Hey everyone, welcome back to my Calculus 1 series. In today's lesson we'll be talking about continuity. So to get right into things, the concept of continuity is based on this one definition and a few things that we can derive from it. But the definition goes as follows. A function f is continuous at a number a if the limit of the function as x approaches a is equal to the function evaluated at that value that we're approaching. From here, we can kind of derive three key things. The first thing is that f of a is defined, which we can also rephrase and say that it's in the domain of f. The next key thing that we can extract from this definition is that the limit as x approaches a of f of x exists. And the final thing, I'd say it's almost a repetition of this, but it's basically this formula right here. So it's that the limit as x approaches a of the function at f of x is actually equal to the function evaluated at that value. So these are the three things that are kind of implied from this definition. And essentially, if we have a function that doesn't meet these three criteria, we then can say that the function is discontinuous. So just to break this down a little bit more, this point right here, I feel like it's pretty self-explanatory. F of a being defined just means that we have a value there. It's not like a hole or an asymptote at that value. There is a specific defined value that f of a has. This next point right here, where the limit of f of x as x approaches a exists, this would mean that the limit from the left side and the limit from the right side both exist, and they both equal to this limit itself, meaning that the graph from both the right side of a and the left side of a is approaching the same value. This means that the graph will be continuous at that point. And lastly, it has to meet this criteria that this limit is equal to the actual value at f of a. And so I feel like these three qualities are pretty self-explanatory, but on a graph we can think of it as f of a must exist. So we can't have, let's say, like a function like this and then all of a sudden we have like a hole right here or something like that. Likewise, we wouldn't be able to have an asymptote at x equals a either, because that would fail this condition right here. And for this point right here, the fact that the limit exists, we shouldn't have anything like this, for example, where we have these like this offset of it's called a jump, where we have this jump and all of a sudden the limit from the left side and the limit from the right side doesn't exist. If we think about it, if we have a valid point, right, like a given point right here, and it exists for that function, and the limit from the left side and the right side of that function is both approaching the same value, it's kind of self-explanatory, but it's bound, the function is bound to be continuous at that point because the point exists, and because through this condition right here, we ensure that coming from the left side and coming from the right side, we're both approaching the same value. So we kind of ensure that the function will be continuous. So now moving on to one-sided continuities, it's very similar to the concept of continuity itself. However, we're dealing with a continuity from only one side of the function. So if you remember back up here at this this criteria right here, I said that because we're ensuring that this limit exists, that means as we come from the left side and the right side of this a value, we're approaching the same value. Essentially, this right here is the condition for it to only come from the right. So as it's written here, a function f is continuous from the right at a number if the limit as x approaches a from the right, so a positive, of the function f of x, it must equal to f of a. Now, the concept of continuity on intervals is pretty simple. Essentially, we can say that a function is continuous on an interval if it's continuous for every number within that interval. So there's not much to this concept of continuity on an interval apart from just a definition. And if you think about it, what it means to be continuous, then if we take a set of points that a function is continuous on, we can say it is continuous on that whole interval. So instead of writing like, oh, it's continuous on like 1, 2, 3, and all the way to like 10, we can just say, oh, it's continuous on like 1 to 10 inclusive. And this is basically just giving it an interval format. But like the definition for that would be like a function f is continuous on an interval if it's continuous at every value in that interval. To talk about the continuity of the combinations of functions, we are looking at when we are combining two functions. So if you go back a couple of lessons, I talked about function transformations and combinations. You can check that video out. I'll add a link to it right here at the top right. But essentially, a combination of a function is when we combine two functions together. So for all the examples that I'm going to be giving, let's say that f and g are functions that are continuous. So if f and g are continuous functions, then we have 5 other function combinations that will also be continuous at, let's say, a, which is within the given interval of continuity of these functions. So the first combination is that f plus g will also be continuous within that interval of continuity for f and g. 2 is that f minus g will also be continuous. 3 is, let's say, cf, where c is a constant. And 4 is f times g, so the multiplication of two functions. Now, I'm not putting the x at the end of it, but maybe I should be just for visual purposes, but essentially it's all the same. And lastly, for number 5, the last one is f over g of x if g of a is not equal to 0. So g of a meaning that like a specific value within the interval of continuity of g. If it doesn't equal 0, then this property, the fifth one, will hold. But if it is equal to 0, again, we're going to get a division by 0 error, so we need to put that constraint on it. So now on to some more useful stuff before we were just dealing with definitions. This is still going to be a definition, but this is definitely a lot more applicable when you're dealing with limits. So we're going to be talking about the composition of functions, essentially one is composed of another function. It's written like this, but you can check out my previous videos and I go all about composition of functions. But let's say we have a function f and it is continuous at this value b, and the limit of this other function g of x is equal to b. Then we can say that the limit of f of g of x, so the composition of these two functions, is equal to f of b. Basically, if we want to translate that, we can say that the limit of f of g of x is equal to f times the limit of g of x. Because we said that b is equal to the limit of g of x. So if we just take this b value and change it to be the limit of g of x, then we get this little formula right here. So essentially, if f is a continuous function right here, and this limit, the limit of g of x at whatever the value is, at let's say x equals a or x equals z exists, then what we can do is kind of move this limit like from the outside of the function inward, and we can apply the mapping that f does to this entire limit. And another point that we can say about function compositions is that f of g of x is continuous at a if and only if f and g are both continuous at a, which is pretty obvious. So lastly, we'll be talking about the intermediate value theorem, and this theorem is like very obvious if you think about it, and I will demonstrate to you visually after the definition as to why this theorem makes complete and absolute sense. But as of now, I'll give you a definition, kind of try to break it down a little bit, and then I will give you a visual example. So here is kind of what the intermediate value theorem is. And for now, let's say that there exists a function called f, which is continuous on this closed interval of a, b. And these square brackets mean that it's a closed interval, so it includes both a and b. And then let's also say that there's this number n that can be any number between f of a and f of b, such that like f of a is not equal to f of b. So the two y values of the endpoints a and b are not equal to each other. If this is the case, then we can say that there exists a number c within this is not a closed interval, meaning it's exclusive of a and exclusive of b, such that f of this, whatever this c is equal to this value that is in between f of a and f of b. So if we think about it, this is like very obvious, and I'll show you why graphically. So let's pretend that this right here is f, this green function, and I've marked the two endpoints. Let's just choose any two arbitrary endpoints such that f at a and f at b are not equal to each other. So as we can see, the values at f at a and f at b are not equal to each other. And essentially what the intermediate value theorem says is that if we pick any value in between f of a and f at b, we will find an x value, or in this case they call it c, that will map to a value in between f and a and f at b. Why this is extremely obvious is because if we think about it, this function starts down here. Let's say that this value is 1 right here and that this b value is at 2, right? So let's look at just this interval from a to b. So we know that the function on this interval starts at 1, the y value of 1, and it goes up to 2, right? And we know the function is continuous, meaning there is no breaking point. So at one point, this function will have to go through every single value between 1 and 2 because it somehow needs to get from a y value of 1, which is right here, to a y value of 2. So no matter how you draw this graph, this function can literally go like this, but eventually it will go back up to 2, or this end value. And if we think about it, because it's continuous, it must go through every single value between 1 and 2. Like, there is no way that this function can possibly skip a value. Yes, it can go outside. It can go outside of these bounds of 1 and 2, but that's not what the theorem is talking about. The theorem says that there exists an x value between this interval of a and b that is in between f of a and f at b, which essentially are the endpoints, like the y endpoints of our function on that interval. So because the function is continuous, it must go through every single value between 1 and 2. It must hit it at least once. As we can see here, it's probably dipping down to right here. It's probably dipping down, but here it starts to crawl up. So we'll start to see, 1.1, 1.2, 1.3, 1.4, 1.5, and it can't miss a single value in between that because the function is continuous. So that's the basis of the intermediate value theorem. It takes into account that this function is continuous, and it essentially leverages that to say that, hey, if we started at this specific start point of f at a, and then we ended up at f at b, and since f at a and f at b are not equal to each other, then because the function is continuous, it must have hit every single y value in between f at a to f at b. Therefore, there must be an x value within that interval that maps to that specific value, which is given by this formula right here, that f at this x value will map to this arbitrary value of n in between these two endpoints. So that's it for continuity. It was a pretty short lesson, just filled with a bunch of definitions, and obviously the intermediate value theorem, which can be used to prove stuff like the existence of roots, and has a few other applications. But that's it for the video. I hope you enjoyed it. If it helped you at all, please leave a like and comment on what it helped you. As usual, if you're new to the channel, please like, comment, and subscribe, and I will see you in another video.